So scientific notation, we're going to be turning large numbers into scientific notation. So the way this is done is you put the dot right, you scan the number from left to right, and when you find a number that is not a 0, you put a number right behind it. So in this scenario, it'd be right here. This is where we're going to put the dot. So this number over here in scientific notation is now going to be written as 1.02. And now the goal is to eliminate all these zeros. So then now this is our new number. And then we're going to write times 10. Now, this is where the decimal point used to be. And this is where the decimal point is. So now you have to display to me how many times you moved it to get to its new location. So this is the old location. 1, 2, 3, 4, 5, 6. So you moved it 6 times. So it's positive 6. It's positive 6 because this is a very large number. Okay, this is 1,020,000. This is a large number. Now this, we know that we're going to be having a point that says times 10 to the power of negative something. Why? Because this is a very small number. It's less than 1. So we know that we're going to have a negative exponent. Now again, you scan it from left to right until you hit a number that is not a 0. The 2. So now we're going to put the decimal point here. So now our new number is 2.28 times 10 to the power of negative something. So now let's look here. So 1, 2, 3, 4, 5. So it's negative 5. All right. Now this one we're doing the opposite. Now, we have to make 4.91 into a large number. How do I know it's becoming a large number? The exponent is positive. So in what direction do I move this dot to make this number larger? To the right. So how many times are we moving it to the right? 8 times. So 4.91, so 1, 2, and then 6 more times. So now I'm going to have 6 zeros. And there's my dot. So it moved 1, 2, 3, 4, 5, 6, 7, 8 times to make it larger. So now this is 491 million. This one. Now this is a negative sign, which means this dot is moving in a direction that makes the number smaller. So it's going to the left. That makes it smaller. How many times is it moving to the left? 4 times. So we know that we have 3, 2, 0, 1 here. So dot is here. So it's moving once and 3 more times. So 1, 2, 3, dot. Let's check where it was and where it is. So it used to be here. And now it moved 1, 2, 3, 4. There you go. So now it's 0.0003201. Perfect. Now here, how do you multiply scientific notations? You simply multiply the numbers. 2 times 3.1. You're going to get 6.1 times, and then you multiply this exponent, 10 to the 5th, times 10 to the negative 2. So the exponents are going to add. So this is 5 plus negative 2, which is the same thing as 5 minus 2 in this situation. So it becomes 3. So times 10 to the power of 3. And that's it. Now remember, if this decimal point, if this would have ended up to be look like this, 61 times 10 to the 3. If it looked like that, what you would have done was move the decimal point one more time to the left and increased this number to 4. All right. Now here, let's do this. 2.6 times 10 to the 5th divided by 2 times 10 to the negative 7. All you do is divide this, which gives you 1.3 times 10. And then you have to subtract these two numbers. So 5 minus negative 7, which is the same thing as 5 plus 7. So that would be 13. No, that would be 12. So 10 to the power of 12. And that's done. Again, if this would have ended up to be 0.13 times 10 to the 12, and I had to move it to the right one more time, this number would have decreased and become 1.3 times 10 to the 11th. So that's question 4. Question 5 and 6, I'm going to do a couple examples. So, the first thing you have to know how to find is the y-intercept. So we're looking for the y-intercept. All you have to do to find the y-intercept is put 0 in for x and solve. So if x is 0, this is 0, the answer is 1, so the y-intercept for this one is 1. So if I put a 0 in this one, it's going to be 3 to the power of 0, which is 1, minus 1. So the y-intercept for this one is 0. So this one is 3 to the power of 0, which is 1 times 2. So this y-intercept is 2. This one is 3 to the power of 0 times negative 2. So y-intercept equals negative 2, because 1 times negative 2 is negative 2. So that's how you find y-intercept. That's pretty basic. Domain in all of these situations are going to be all real numbers, because there's no limitation to x. I can put any real number in for x and it's going to be acceptable. So for the domain, because it's asking what are all possible x's, it's going to be all real numbers. Okay, same thing here. Domain here is going to be the same. Domain here is going to be the same. Hopefully you're seeing a pattern here. And the domain here is going to be the same. Now, for this one, the range means all possible y's. Now, no matter what x I put into here, okay, if I put a negative sign, it's just going to make this very small. What it's never going to make it is 0. And what it also is never going to make it is a negative number. So this will never become a negative number, and it will never become 0, which means the range is all positive real numbers. Now this one, the range, now we already know that the range is all positive numbers. It'll never touch 0. But if you subtract 1, that lowers the range one entire number. Now remember, when you graph these, this is exponential growth, so it looks something like this. Okay, so it'll never touch 0, but if I subtract every single one of these dots, it will go lower than 0. The number it will never touch is negative 1. So the range here is all real numbers greater than negative 1 now. So the range has shifted down. All of this, okay, this is the new one. All of this has shifted down 1. Okay? Now this next one, this is being multiplied by 2. That doesn't change anything. The range is all positive numbers. All multiplying by 2 is makes it go up faster and go down slower. So it's going to be times 2, right? But it's still going to keep on getting closer to 0. It's just going to take a longer time, and it's going to go up much faster. So that line is going to look like this, there we go, like something like that. Okay, it's just going slower down, but it's still going to go down to 0. It just never will get to 0. It'll get really, really close. So the range doesn't change at all if I multiply it by a positive number. Now, if I multiply it by a negative number, the range changes completely. Because now every single one of these numbers of the original has now turned into a negative sign, so it looks like this. So now the range is all negative real numbers. Okay, so if it's just a regular exponent, positive or negative, this is the domain, this is the range. But if I subtract something, the range goes down. If I add something, the range would go up. Domain stays the same. The y-intercept you should be able to find. This one, if I multiply by 2, nothing changes. Multiply by a positive number changes nothing for the domain and range. Now, if I multiply by a negative number, the range does change because now everything that used to be positive becomes negative. Hopefully that made sense. Graphing is also very simple. You start putting numbers in and start making dots. Once you get the pattern down, it's pretty obvious. For 7 and 8, exponential, yes or no. This is going up by a constant pattern, and if this is going up by a multiplying, so here, how did the 6 turn into 12? It multiplied by 2, right? Multiplied by 2. If it's going up, it has to be multiplying. If it's going down, it has to be dividing. Multiplied by 2. This is being multiplied by 2. This is also being multiplied by 2. So this is multiplying by 2. So is it exponential? Yes. It's like 2 to the power of something. Now there might be another variable here, but this is the exponential. So yes, this is exponential. If it doesn't follow this pattern of multiplying by 2, like let's say it was adding by 2, that would not be exponential. If it was subtracting by 2, that would also not be exponential. Now, if it was dividing by 2, it would be, because it's the same thing as multiplying by a half. So it's multiplying by something consistently if it's dividing by 2. So this is exponential, yes or no. For number 9, is it geometric, arithmetic, or neither? Geometric is the same thing as exponential. It has to be multiplying by something every single time. So this is multiplying by, so it's going down, so it's multiplying by a half every single time. So this is geometric. If it was just adding a half, like it said 1/2, and then it said 1, and then it said 1.5, and then it said 2, and then it said 2.5, that would be arithmetic. Okay? For this one, complete the pattern. All you have to do is notice the pattern and then finish it. So this is multiplying by 4, multiplying by 4. So you have to multiply by 4 again, which would be 120 plus 8, so 128. And then multiply all this by 4, so it's 400 plus 80 plus 32. So that's 400 plus 80, that's 480. Plus 32 is 512. So that's 512. And then this times 4, you get the gist. So you finish the next 3 numbers of the pattern. That was very simple. The formula for this one, which is very simple, it's a to the n equals a to the 1 times r to the power of n minus 1. Very simple. So if I want the equation for this, a to the n, all I do is put the first answer in the sequence, which is 10. Then the rate, so how is it getting from here to here, from here to here? It seems as though it's multiplying by a half, but a negative half. So multiplying by a negative half. And then n minus 1. And that's it. That's 11 and 12. Write the pattern down. Very, very simple. Hopefully that makes it easy. Good luck, guys.